Lowercase f is the remainder function, so let's try to calculate f starting with n equals 20 and identify the maximum values. We'll take k up to 20 divided by 2, which is 10, and calculate the remainders. There's no remainder when 20 is divided by 2. Here we get a remainder of 2. 20 is a multiple of 4 and 5. It's 2 more than a multiple of 6, and 6 more than 14, 4 more than 16, 2 more than 18, and it's a multiple of 10. Looking for the winner, the maximum value of f, that's 6, when k is equal to 7. We'll try again for n equals 21. This time, we'll ignore k equals 3 and 7 because that divides 21 evenly, and we'll get f equals 0, so not a winner for those values. And we stop at n over 2, where k is an integer. 21 is odd. It's also 1 more than 20, 1 more than 20, 3 more than 18, 5 more than 16, and 1 more than a multiple of 10. The winner here is 5 when k equals 8. Let's try n equals 22, and since it's a multiple of 2 and 11, we'll skip those values of k. This is 1 more than 21, 2 more than 20, 2 more than 20, 4 more than 18, 1 more than a multiple of 7, 6 more than 16, 4 more than 18, and 2 more than 20. Our winner here is 6 when k is equal to 8. I continued calculating f for values of n up to n equals 29, and I found the maximum values. Let's summarize the results in a single table. We're going to track n, the maximum value of our remainders, and then the k that gave us the maximum value. So when n was equal to 20, our maximum f was 6, and this was when k was equal to 7, and so on. 21 gave us 5 when k was equal to 8. It looks like we can see our pattern. Our results come in groups of 3, with consecutive values of capital F of n for the same value of k. If we were to generalize this, we would start with a multiple of 3, and our maximum f is m minus 2, and this happens when k is equal to m plus 1, and so on, adding 1 to the remainder for the next 2 values of n. At this point, when we can see the pattern, we can go ahead and find the sum of all these f of n's as n goes to 100. But before we do that, let's just verify that this pattern continues. So first of all, in order to calculate the remainder, when we divide 3m by m plus 1, we can write it like this. I can write this as a multiple of m plus 1, and then we have an extra m and a minus 2. This gives me a quotient of 2 and a remainder of m minus 2. So this is always going to be true. We can do this with 3m plus 1, or just note that since we're adding 1 to the dividend, we're going to add 1 to the remainder as well. So our remainder is m minus 1. And again, adding 1 to the dividend adds 1 to the remainder, so this is equal to m. So this is always true. But the next question is, will these values always be the maximum and therefore capital F? So first of all, we'll find f of these 3 numbers when divided by a number k, when k is some number that's less than m plus 1. Let's try k is equal to m. So f of 3m and m means we're going to find the remainder here, which is 0. Adding 1 to get 3m plus 1 and dividing by m gives us a remainder of 1. That's 0, 1, and 2. And our values of n are such that m is greater than or equal to 7. So these numbers are always going to be less than m minus 2, m minus 1, and m. Let's try k is m minus 1, and we'll find the values of these functions. We'll take 3m and divide by m minus 1. We can rewrite 3m as 3 times m minus 1 plus 3. This gives us a quotient of 3 and a remainder of 3. So our remainder function gives us 3, which is too small. Similarly, our remainder function for 3m plus 1 and m minus 1 is going to be 1 more than that. And for 3m plus 2, it's 2 more than 3, or 5. We can also check our data. For example, if you look at numbers that are 1 more than a multiple of 3, we see a 1 and a 4 here, a 1 and a 4 here, and a 1 and a 4 here. So it checks out, as we predicted here, a 1 and a 4. Let's see what happens when k is even smaller, less than or equal to m minus 2. Remember, our f is a remainder function, so it's always going to be less than the divisor, or in this case, less than y. So when we take f of 3m and m minus 2, this is going to be strictly less than m minus 2. And same for our other dividends. And we're less than m minus 2, which is less than the results that we got when k was equal to m plus 1. Now we're going to check to see if our maximum remainder function is going to be greater than what we had previously, m minus 2, m minus 1, and m, for larger values of k. First, we note in the problem statement that our divisor is less than or equal to n over 2. Multiplying both sides by 2, n is greater than or equal to 2 times k, which means n is 2 times k plus some value r. So when we take n and divide by k, we can substitute. We're left with a quotient of 2 and a remainder with r over k. Note that as k gets bigger, our quotient will not be less than 2. And this makes sense because k is not going to be greater than n over 2. So if we take a multiple of 3 and divide by k, the greatest that the quotient can be is 2. So I'll put 2k over here and then subtract 2k to balance. And I'm left with a quotient of 2 and a remainder of 3m minus 2k. So our question now is, will 3m minus 2k ever exceed m minus 2, which was the value that we got for 3m comma m plus 1. Let's start with the condition that we're given, that k is greater than m plus 1. Let's multiply both sides by 2, so we have 2k is greater than 2m plus 2. We'll subtract 2k and subtract 2 from both sides. And finally, I'll add m to both sides. So we have m minus 2 on the left and 3m minus 2k on the right. This was our remainder, and we note that our remainder is less than m minus 2, which was the solution we got when k was equal to m plus 1. To find f of 3m plus 1 and k, we'll just add 1 to this remainder, and we note that this is less than m minus 1, which was our other solution, and adding 2 means we add 2 to the remainder, which is going to be less than m. So we won't exceed the remainder that we got when k was equal to m plus 1. So let's go ahead and add our numbers. We're supposed to sum capital F of n as n goes from 20 to 100. Our first number here is 6, and then we have this triplet 5, 6, 7, and then the next triplet of consecutive integers, and so on. We're looking for n is equal to 100 for our last term. We note that this is one more than a multiple of 3, so I'll write this as 3m plus 1, gives us m is equal to 33. For numbers that are one more than a multiple of 3, like 100, our value of capital F is m minus 1. That's 33 minus 1, or 32, for our last number. F of 99, since it's a multiple of 3, is going to be m minus 2, or 31. Those are our last two terms. And then the triplet that occurs before that begins with the previous multiple of 3, or 30. So this is 30, 31, and 32. Take the 6 separately, and I'll go ahead and add these two to get 63. This triplet is 3 times 6, and this is 3 times 7, and so on to 3 times 31. Adding these two, I get 69. I'll factor out the 3, and then we get these consecutive integers. I'll add these by taking the first and the last, finding the average, and then multiplying by the number of terms, which is 26. Multiplying this out and adding up, we get 1512, and the problem wants the mod 1000 residual, which is 512. If you'd like me to solve any other math contest problems, please leave them in the comments.